Since the earliest epochs of humanity, dating far before the beginning of civilization, over 100,000 years ago, we have looked up and wondered, why are there stars in the sky? Where did we come from? Is in pondering these deep, deep questions that humanity has sought answers. In looking up at the stars, different cultures associated different myths or really different stories about the origins of the stars and their groupings. Uh, in this image, you can see, and this is really Stellarium, which we'll talk about in a little bit. You can see the Big Dipper, or in the Western or the International Astronomical Union parlance, we have Ursa Major, the Big Bear. And so if I go ahead and turn on the constellation lines, then admittedly, I don't really see much of a bear still, right? The Dipper part I see pretty well, but I'm quite trained or used to it at this point. If we had the constellation labels, you can see that I wasn't joking about the Big Dipper really being part of Ursa Major. And then if we turn on this constellation art, then somewhat fancifully, but somehow we do in fact have Ursa Major. And these two pairs of stars I have always thought of as being basically the legs of Ursa Major. Um, Although you can see that this pair here is, we'll see if I can actually get this to a point where I'm trying for it to point, but I guess we'll give up on that. So regardless, we have Ursa Major. Now, as we'll talk about much later in the course, the Big Dipper is really a important region of the sky for cosmology. The Hubble Deep Field, which allowed us to really probe some of the first galaxies and first really patch of the sky after the Big Bang, was looking within the region of the Big Dipper's handle, or really the tail of this big bear. Now, if you know anything about bears, usually they have short, stubby tails. So, the natural question would be, why does this bear have such a long tail? And if we rotate in the sky a little bit, there we go. And we can see that Ursa Minor, the little bear, has an even longer tail. Now, the Greeks had their different stories. Actually, every different culture had kind of a different story. But in the Greek tradition, the reason why we have Ursa Major and Ursa Minor having long tails, the story goes that one day Zeus, from up on his perch in Mount Olympus, spotted a beautiful girl down in Athens. And becoming enamored, Zeus decided to go down to Athens, kind of strut his stuff, and the woman fell madly in love with him. And they had a jolly good afternoon. Hera, from up in Mount Olympus, Hera is Zeus's wife in Greek mythology, another one of the gods, spotted Zeus in the act of infidelity and was not so pleased about this. Later on, Zeus went back up to Mount Olympus, took a nap, and Hera, enraged about this seductress of her husband, went down to Athens and turned the woman into a bear. And that bear started rampaging through Athens. The people came to the streets and prayed to Zeus, please, please save us from this bear. Zeus, hearing the cries of his people, awoke from his nap. He went down to the city of Athens, grabbed the bear by its tail, went down to Athens to kill the bear. Zeus, in looking in the eyes of the bear, recognized the woman that he loved, and I guess Zeus was quite a character, although he only knew her very briefly. He, I guess, loved her very deeply. So, to immortalize his love, he grabbed the bear by its short, stubby tail, flung the bear around his head and into the sky to immortalize his love. And in flinging the bear into the sky, its tail got stretched out. And then And then the bear gave birth to Zeus's child, Ursa Minor, which somehow inherited the long tail. So this is one story of the origins of these constellations. In this class, we're going to go into cosmogony, a story of the origins of the universe as told by different cultures, and then we're going to start making our way towards the birth of science. So let's go ahead and switch gears, and I'll go ahead and say welcome now, everyone, to back to Physics 135, the first 3 minutes for class number 2. In overview, we're going to start with these origin stories, not just of the constellations, but really of the entire universe, as told by 4 different cultures, although, again, every culture has their own origin story. We're going to talk about so-called scales to weigh philosophies, and these will be important really when we're talking about comparing different models, as well as for understanding the almost tectonic shifts in human thinking over the past few thousand years about our own origins in this modern scientific era. And last, we'll talk about really the birth of science, really the emergence as a branch of philosophy. Now, one thing I'll mention is that just like I'm encouraging all of you to use different AI models for your reading assignments, in this course, I've started to dip my toes into trying to use AI to make these slides a little bit more aesthetic. So last class, you noticed that they were all like blank white slides. Today, you'll see that I went through 3 different iterations. And please let me know if you like the AI kind of assisted slides. I'm kind of artistically challenged or aesthetically challenged. So I think that they do look quite nice, but if you don't like them, let me know. I think it overall took me longer, unfortunately, with the AI assisted slides compared to if I was doing this manually in a much more basic way. And I'll explain that as we go on. So for this first portion of class, we'll kind of call this myth, music, and measurement. So we're going from ancient cosmogonies all the way up to really kind of pre-science, if you will, in terms of the rise of mathematics and specifically geometric astronomy. So in terms of these origins, we're going to talk about kind of the why of creation and compare 4 different cultures, the Greek, Chinese, Indian Vedic, and Australian Aboriginal myths about cosmogony or how the universe was made. We'll move on and talk about Pythagoras and the mathematical structure of the cosmos being all fundamentally musical ratios. And then third, we're going to get into the measurement side of things. And there are 3 key figures there. We'll really be focusing, admittedly, on Eratosthenes, as well as Aristarchus. So, in terms of these creation myths, the first myths we'll go into are the Greek, and so we'll be talking about Hesiod's theogony and about really this tendency to associate anything that was unknown with a deity in the Greek tradition. And this dates back not quite 100,000 years, like the origin of humanity's consideration of the skies. There are cave drawings that go back, we think about that far. But only, about 3,000 years ago, or a little shy of 3,000 years ago, one of the important Greeks, Hesiod, came up with really a codification for their creation story. In the beginning, there was so-called chaos. This was a void that existed before anything was made. And then at a certain point, there was both Gaia and Uranus, the earth and the sky. And these were separated through not just like something metaphorical, but there was a barrier between the earth and the sky. And in terms of the barrier, this had to do with some of the different gods that were formed. So the Earth was originally considered this flat disk with a massive river, Oceanus, which basically um, cut things off from the heavens. And then um, just as far above the Earth as were the heavens, so below the Earth there was so-called Tartarus, or what we would today call hell. And the idea was that this is where Hades and kind of the god of the afterlife did his thing. And then in terms of the so-called heavens, the idea was that there is this huge dome where Atlas was supporting the earth perpetually. And basically, this is something that was unreachable by mortal man. You'd have to go beyond the edge of the known world, beyond Oceanus, this earth encompassing river. Okay, and then switching gears for Chinese cosmogony, we have something in a way that's similar, but certainly with its unique aspects. So, similar to the Greek tradition, where the origins started with chaos, similarly in the ancient Chinese tradition, there is this so-called cosmic egg that was how all existence began, and that cosmic egg had chaos. And then from within that chaos, there was this giant called Pangu who grew for 18,000 years. And as Pangu emerged from that chaos egg, the lighter parts of that egg, which he ripped off, rose and formed the sky, whereas the heavier parts sank and formed the earth. So we have the creation of yin, which I guess was the earth, and yang, which was the sky. And Pangu was kind of the barrier, if you will, kind of similar to Oceanus, but also kind of similar to Atlas, if you will. And Pangu grew about apparently 10 feet every day in order to keep the sky from falling onto the earth. Sounds almost like Chicken Little in terms of the sky potentially falling onto the earth is what I thought of here. All right, and then so this is the starting point, and then there's a additional episode. So after Pangu was made, there were all these different gods that arose, kind of similar in the Greek tradition, where the Zeus and Hera that we were talking about were kind of the second generation of gods that reigned on Mount Olympus after killing their parents. There is, in this Chinese tradition, there is similarly a war between gods, and at that point, the pillars holding the sky collapsed. And in the Chinese tradition, Nua, the mother goddess, was responsible for repairing the universe for two main things. One, she took these five colored stones and patched up the sky. And two, she kind of sounds a little gruesome to me, but she took a giant turtle, cut off the legs, and used those to keep the heaven from crashing back down to the earth again. So really, there are two key figures in this Chinese tradition, Pangu and Nua. Although, again, the Chinese cosmogony contains a lot of different gods that we're not talking about. Just like in the Greek tradition, there were many, many gods beyond the few that I have mentioned. Okay, and then one thing to kind of mention is that there are actually many different uh, sort of cultures in the subcontinent as well as large country of India. So we're going to talk about the Indian Vedic cosmogonies, um, but this is just one kind of example. There are many different cosmogonies in for Indian people, is my understanding. Okay, so in the Vedic tradition, there was, and excuse me for pronunciations that may be going awry from this part forward, Nasadiya Sukta. who was a so-called agnostic inquirer. So the idea dating back now a little bit older than that Greek tradition, which was from like 800s or so BC, almost 700 years earlier, the we have as quote, then was not non-existence nor existence, who knows then whence it first came into being. So I think of this as being similar to this primordial chaos in the Greek and Chinese traditions, but you can reject that. Maybe it's totally its own thing. And so this is going into the Indian Vedic gods coming after creation with some sort of like coming into being, in other words, some first cause. So, in essentially all these traditions, there is some origins to the universe, although in this case, it's a little bit more hard for me to parse, admittedly. And then there's a kind of almost separate tradition, this Haranyagarbha, or the Golden Womb. And in this case, the idea is that creation is a cyclic process, similar to the story that in this Vedic tradition still, that in terms of what is supporting the earth, there is a giant turtle. And what is supporting that giant turtle, there is another giant turtle, leading to this phrase, it's turtles all the way down. In a kind of similar way, the idea is that creation is an infinite process and it goes through cycles. The universe expands and then collapses. And the idea of Brahma's day is that the cycle lasts about 4.32 billion years. So a very long time, especially considering the 15,000 years of the Chinese tradition. And interesting thing is that this is a pretty similar number to the age of the Earth. Maybe this is a coincidence, or maybe there was uh, rather a lot of um, very sophisticated mathematicians and physicists back then that we just otherwise haven't heard of quite as well. All right, and next for the Australian Aborigine cosmogonies, one thing that's very, very interesting for the Australian Aboriginals is that rather than finding constellations with the stars, they actually looked at cosmic voids. Now, just to get into the origins of the universe, um, their tradition is a so-called dreaming. So there is some timeless era where there were ancestor spirits, and through their singing, they ended up creating the earth and creating all of existence. And so I think that this is really kind of interesting. So the idea is that the land and the sky are really encoded through these so-called song lines, and that all of existence is like a kind of a music book, if you will. Um, And in that case, there's this correspondence between geography in terms of valleys and hills and astronomy being related to that kind of cosmic singing that created everything. So again, kind of unlike our Western traditions and most cultures that I'm aware of, honestly, they identified constellations through the voids or the dark regions, and we now know that those are dust clouds in the Milky Way. So one of their constellations is so-called Emu, and this is related to when it's the proper season for emus on Earth to be laying their eggs. And so, in other words, they had something that was very much related to life on Earth as reflected in the skies. And that's something that, although again, the kind of cosmic voids is dissimilar from a lot of different traditions, as we'll be talking about rather more next time, there is a very close overlap between astronomy and people's everyday lives, or in other words, the consideration of the cosmos and people's everyday lives in the ancient world. All right, so in summary, we've considered these four different cultures' cosmogonies. For the Greek, we talked about Hesiod's theogony, about chaos, and then the separation of Gaia and and Uranus, and really the development of the gods was almost a way of identifying really different causes related to nature ultimately. And in the Chinese tradition, there's some similarities here. We have a creation of earth and sky from some original chaos. In the Indian Vedic tradition, there's also this maybe creation event from chaos. It's rather more sophisticated in terms of the cosmology, or at least the philosophy behind this. And then for the Australian Aboriginal tradition, again, the idea is that there was this cosmic singing driven by these ancestor spirits. Okay, so we've talked about the ancient myths. Now, of course, this is a physics course, so we need to move beyond these myths and try to get to science. But it's very important to consider one of the things that we'll talk about is the development of modern cosmology. And it's interesting that in many of these ancient traditions, there is a creation event. Now, this is a bit of a preview, but probably most of you have already heard that our modern theory of cosmology is called the Big Bang Theory, in which we believe that the universe was created at a single point in time, if you will. And we'll talk about why the Big Bang Theory faced such strong philosophical headwinds. In some ways, that was still repercussions of pushback against these ancient myths. So, moving on, in terms of how we assess how relevant or how useful philosophies are, we're going to start to transition from these myths into logic and the beginnings of philosophy, which is related to the birth of science. So, in terms of these different traditions, we have many different stories that have explanations for the world around us. But then the question arises, how do we decide which of these stories we live by? And in this class, we're going to work with 3 different criteria. Admittedly, if you go deeper into philosophy, there's several more, anywhere between 5 to 7 to potentially even more criteria that philosophers consider. But the main ones for this course will be explanatory scope, explanatory power, and simplicity. So in terms of breaking these 3 down, for explanatory scope, you can think of this as being sort of like a Swiss Army knife. So the scope is related to the breadth of a theory or a model. If you have a theory that has a large or high scope, that means that it's explaining a wide variety of items. So one example would be the Aboriginal Dreamtime has a very large scope. It is trying to explain everything about the geography here on Earth as related to this cosmic singing of these ancestor spirits. So, and not only about geography, it's also trying to explain like how we live our lives with certain laws. So the idea is that the Australian Aboriginal Dreamtime myth is all encompassing. Now, having as large of an explanatory scope as possible is a benefit, like to a theory. It's how one way that we judge it, but it's not all encompassing. Really, just explaining why without any precision or quantitative measure is, we'll say at least for this class and generally in science, insufficient. And this is admittedly true not just for science, but for a broad range of philosophical modeling. Now, again, the Australian Aboriginal myth had explanatory scope, but it lacks explanatory power. The idea with explanatory power is think of a laser pointer. For a laser pointer, it only does one thing, right? So it doesn't, whereas a Swiss Army knife, you have maybe a pair of scissors, a knife, you have you have a corkscrew, you have many different things that you can use a Swiss Army knife for. A laser pointer only does one thing. It just shines a beam of light. But a laser pointer can be very useful, and it can be very, in terms of how that light is made, that happens very precisely due to physics that we won't really be talking about in this course. But in terms of understanding explanatory power, if explanatory scope is like a floodlight encompassing everything, explanatory power is again more like this laser pointer that's shining in one very particular direction. And we'll talk about Eratosthenes a bit later in this class, but just as one example to tie this into the reading material that you should have already done at this point, Eratosthenes said that not only was the Earth round, but he calculated the circumference to very high accuracy. So, in other words, this demonstrates that the model of Eratosthenes had explanatory power. It had a very precise value. And the third criterion that we'll consider when we're weighing different philosophies or different scientific theories is on simplicity. And this goes back to not nearly as long ago as those ancient myths, but back to well into the Middle Ages or the Dark Ages, so close to 1,000 years ago at this point. Sir William of Ockham was quoted as writing, "Entities should not be multiplied beyond necessity." Or in Einstein's parlance, we should have a scientific theory which is as simple as possible while still explaining the data. So, for an analogy, if you hear hoofbeats, then that could mean a number of things. It could be that there are horses, it could be that there are zebras, maybe it could even mean that there are elephants, it could mean a lot of different things if you just hear hoofbeats. Now, in the US, though, there's really not a lot of zebras galloping around. So it'd be pretty reasonable to conclude that when you hear hoofbeats, you could expect to see horses. Now, if you were right outside of a zoo or so, that might change that a little bit, right? So keep in mind that these assumptions that we're making related to simplicity, when there's limited applicability, like, okay, hoofbeats means horses, that's limited to whether you're near a zoo or not. It's limited to are you in Africa or not. We want a theory that is as broadly applicable as possible, right, in terms of explanatory scope. So, in some ways, simplicity and explanatory scope are in contention with each other. Now, surprisingly, it seems like simplicity is a driving factor of the universe, and that the simpler explanations tend to win out, but this is not universally the case. Really, this is our third criterion in order of importance. We need something that has explanatory scope and power, and then when it comes down to the tiebreaker, really, we'll lean a little bit more into simplicity. All right. And then in terms of really coming to grips with the rise of philosophy and therefore the rise of science, I think it's fun to talk about some of the ancient Greeks that were pondering the universe, trying to make sense of physics. In other words, trying to understand motion and dynamics. So Zeno of Elea was a ancient philosopher. If you're interested in reading more about him, there isn't very much that survived. If you read Plato's works, then Zeno comes up in some of the Socratic dialogues. And Zeno was a philosopher that belonged to Parmenides' school of thought, which is that the universe is ultimately one, and all division or cases of apparent multiplicity, in other words, the concepts of me versus you, are all illusionary, ultimately. And if everything is oneness, then in this Parmenidean school of thought, there cannot be any motion. So Zeno came up with a couple of different paradoxes to try to prove that motion is impossible. In other words, that if there is motion, necessarily contradictions arise. And these are called paradoxes, not contradictions anymore, because there are certain resolutions to them. Now, in one of Zeno's paradoxes, the idea was Achilles, the fastest Greek, according to their tradition, Achilles was a hero that fought in the Trojan War, and you'd read about him if you read the Iliad by Homer. Now, Achilles, again, fastest Greek in the ancient world, or fastest man alive. Um, Achilles had a race with the tortoise, which is an iconically slow animal. Uh, in this, uh, so traditionally, a person would say that, okay, Achilles is the fastest person. Achilles has to win this race. Zeno said, okay, suppose that the tortoise was given a head start. Achilles is very confident he'll win. He gives the tortoise a head start. And then let's analyze their motion. Let's say that Achilles is trying to catch up to that tortoise. Let's say that the tortoise is, say, 10 feet beyond Achilles. And Achilles runs at 10 feet per second. The tortoise runs at 1 foot per second. After, let's say, a tenth of a second, the tortoise has moved 0.1 additional feet. And in that time, Achilles would have traveled 1 foot. So Achilles is, it seems like, catching up to the tortoise, but the tortoise is a little bit beyond where it started. The idea is that if we decompose this into not into a tenth of the original, not into 1/10 of a second, but say, well, hold on, let's say that during that a tenth of a second, we divide that into a 20th of a second. Then Achilles has only moved 0.5 feet in that case. The tortoise has also moved a smaller amount, but then Achilles is farther from the tortoise's starting point. And if you divide that further and further and further, you could do that infinitely, and therefore Achilles will never catch up to the tortoise. So that seems to pose a problem. Another one of Zeno's paradoxes was this idea of a motionless arrow. And again, this is before the development of physics, but in this additional parable or story by Zeno, suppose that Achilles shoots an arrow, and we would say that the arrow moves um, through space to hit its target. And Zeno wants to say that that motion is illusory, or is an illusion. And his argument goes that at any given moment in time, the arrow is at one specific place. And therefore, he says that if the arrow is in one specific place, then it's not moving at that specific moment in time, since it's not going from place to place. And then Zeno says that if time is just a whole bunch of these snapshots, and the arrow is still in every single snapshot, then the arrow never moves. Now, if you've taken any physics class before this, then this might seem kind of laughable because our definition of motion, in other words, velocity, is related to a change in space divided by a change in time. So change is a fundamental component of motion in modern physics. But that wasn't at all clear back 2,500 years ago or so. So, in other words, Zeno's claim was that, all right, we have not just this motionless arrow, but what took rather longer time to figure out, admittedly, was Achilles and the tortoise. If motion is impossible according to logic, but we see motion, then it must be that our eyes are broken. Or, in other words, our eyes are not trustworthy. Now, in terms of kind of conclusion here, Zeno's paradoxes have negative explanatory power. They're explaining basically how reality doesn't work, right? So they're using these contradictions to say that something is not the case. So it's really all in negation. Now, in terms of resolving Zeno's paradoxes, really we just need calculus or quantum mechanics to resolve both of them. Those go a bit beyond the scope of this class, but just know that there are solutions. In terms of explanatory scope, Zeno's paradoxes are quite large. They, cover all of space and time. And one of the interesting things about Zeno's paradoxes is really, in my opinion, the um, boom it gives towards quantum mechanics, particularly in terms of Achilles and the tortoise. Now, in summary, though, I want to point out that, okay, we have this so-called philosophical proof, but it turns out that when we have more complex tools, we're able to resolve that. What if we don't have, or we're not sure what tools we might need to resolve a philosophical proof? That suggests that, at least in this class, we're going to need to focus on measurement to really be our placeholder. We're not going to end up concluding that our eyes are broken scales. I mean, it is important to consider the limitations of human measurements, but we will try to be as quantitative and precise in our measurements as possible, and we'll lean onto those. All right, and now kind of developing from these Greek traditions, we're going to go into some of the origins of mathematics. So you've hopefully learned in the past, the expectation is that you have a high school math background about the Pythagorean theorem, that if you have a triangle, you can figure out the hypotenuse of that triangle as being the square c squared is equal to a squared plus b squared. And that so-called Pythagorean theorem dates back about 2,500 years ago. Pythagoras of Samos was really one of the leading mathematicians, and he believed that math was really related to everything or could explain everything. And not just in terms of triangles and geometric shapes that were abstract, but in terms of our everyday lives. Pythagoras was one of the key figures in the physics of sound and music. That's another course that's taught at PFW, Physics 105, that I've taught in the past. And the idea that Pythagoras came up with is that if you take a length of string and that if you cut it in two, you end up going up an octave. So you go up from middle C up one octave to the next frequency of C. If you take string lengths in somewhat different ratios, instead of cutting in half, you do a 3:2 ratio, you end up with a different but still pleasant note or consonant note. It's a musical fifth, and similar for the ratio 4/3. And these are the simplest fractions that you could form, right? 2:1, 3:2, 4:3 are the most beautiful sounding musical notes, or the most consonant. And Pythagoras suggested that this is not just applicable to music or the earth, but that really the laws of mathematics apply to the entire cosmos, and that the orbits of the planets could be perhaps explained also in these ratios, and therefore there is this kind of cosmic singing of the planets. Now, if you can imagine just a single middle C being played uh, without end, I think that that'd be a little maddening. We'll talk about the development of this cosmic harmony as moving forward, and not just a few thousand years ago, but up to today. And thankfully, the modern idea is that there is not just a single note being played infinitely. So quite more of a not just cosmic harmony, but really a full symphony or full musical song, somewhat more of in the Australian Aboriginal tradition. All right, so this is one of the key moments that really pushed us towards science. And around the same time, interestingly enough, Thales of Miletus made a prediction, or at least supposedly made a prediction, for a solar eclipse. And that wondrous event of a prediction made not invoking the gods, but by human intuition as well as ideally some logic, was called the birth of science by one of the great science writers and really science fiction writers, Isaac Asimov. So moving forward, in terms of Pythagoras and cosmic harmony, just to relate this back to our three criteria. So Pythagoras's theory of cosmic harmony, it has simplicity. Everything is music. It has simple ratios, has very large scope. It's meant to apply to everything, but there's not much power. It doesn't really explain or make predictions for how the planet's orbits might change through time. All right, and now into again the birth of science. So I mentioned Thales of Miletus predicting this eclipse. As we move forward a few hundred years, um, or a few decades at the very least, we come upon Anaxagoras, who could be called the first scientist or first physicist. So Anaxagoras made the claim that there was not just Helios that was, or not just a god that explained the sun, but claimed that there was this red hot mass of metal and had a particular size. And Anaxagoras said it had to be larger than the Peloponnese. In other words, larger than this little tiny patch in Greece. But still, this was a start. And similarly, Anaxagoras claimed that the moon was similar to Earth. It would have its mountains and valleys, and interestingly, um, predicted that the moon reflects the sun's light, which is why the moon goes through phases. And Anaxagoras, kind of building off of Thales of Miletus, was able to come up with explanations for why there are solar and lunar eclipses. Moving forward from Anaxagoras, and this is just basically the same information, but a different diagram here. I guess I'll go ahead and pause a little bit here and say that I mentioned that I went through a couple of iterations of AI, and you might have noticed that the slide kind of formatting has changed occasionally. Um, in some cases, I went with iteration one. In some cases, I went with iteration two. And then there was also a third iteration that you might have noticed. Um, moving forward from Anaxagoras, Eratosthenes was really one of the key figures. And what he found was that the shadow that was cast by a pole was different depending on its location on the Earth. So, going into the story in a little bit more detail, although you have to read the book for a much more, I'd say, compelling narrative. So the idea was that there is this well in Alexandria, and the light from that well only reflected really at noon. And Eratosthenes realized that the fact that the well water at the bottom only reflected at a certain specific time of day, it was noon on the summer solstice, meant that the light had to be traveling really a very large distance, in other words, basically parallel to the Earth. And so what he did was he did really an experiment, and in observing the angle that the sun shadow was cast at two different regions in Alexandria and Syene, which were known to be separated by 5,000 stadia. It's a little bit debated what the best conversion between these Greek stadia and our modern units of distance should be. But Eratosthenes calculated or suggested as a result of this experiment that the Earth is a sphere and it has a circumference that was able to be calculated from really pretty simple geometry based on measuring the angles and knowing the distance between those two cities. And the circumference he came up with was 250,000 stadia, which happens to be very close, in fact, to the modern value. Okay, and then we have, again, another diagram. And excuse me, it was well at Syene, not at Alexandria, and then we have an obelisk at Alexandria. Okay, and then just kind of moving forward. So in terms of the math in this course, again, the idea is that you'll need to work with some math, but it's going to be pretty simple math. So in terms of the math here, for 7.2 degrees, if we divide that into 360 degrees, 360 degrees in a circle, we get exactly 1/50th. So that means if we know the distance between those cities, then we can multiply by 50 to get the circumference. So 5,000 times 50, we get 250,000. So hint, hint, as far as your next quiz goes, if a different world was measured to have a different distance between their cities with the same angle, you might be asked to calculate the circumference. So pretty simple math for this class. And in terms of comparing Eratosthenes' value to the modern one, it was very, very close. This is 1 or 2% accuracy using just shadows and geometry. So really a triumph in terms of human ingenuity with very simple tools and methods. And then Aristotle actually also supposed that the Earth was a sphere, but admittedly didn't use quite as sophisticated of a technique and came up with a much larger degree of error. So remember that explanatory scope and simplicity are not sufficient. Explanatory power, in other words, high degree of precision, is a very, very important criteria for how we weigh the scales of different models or theories, particularly for scientific theories. All right, and then in terms of moving beyond the Earth, Aristarchus was the first that was able to come up with a scale for the sun and the moon. And he similarly used a geometric method. And the idea was that when the moon was exactly at its so-called half phase, in other words, first quarter, third quarter, last quarter, depending on how you want to phrase that, he measured the angle between the sun and the moon. And his angle he measured was 87 degrees, which is very, very close to the modern value of 89.85 degrees. In other words, he really should have come up with 90 degrees. And although his measurement was a bit off because, again, not super sophisticated equipment, his methodology was straight on. It's still like a very reasonable way to approach this problem. And Aristarchus showed that the sun was quite a bit larger than the Peloponnese. Instead, the sun had to be much, much larger than the Earth. And this gave some support towards a sun-centered system, which we'll talk much, much more about this upcoming week 2, during our lecture then. So in terms of the scale, the idea was that basically with time, the ideas as far as how big the sun was became bigger, bigger, bigger. At first, the sun was just thought to be, a fraction of the Earth in size. Now, in terms of why Aristarchus's heliocentric theory didn't gain traction earlier, one issue is that it really didn't have very much explanatory power. Although it did make a prediction for the size of the sun, it didn't really predict much else. In particular, it didn't seem to do any sort of difference in terms of the size of the planets. And unlike for Eratosthenes measuring the Earth, there wasn't really any additional way to double check that Aristarchus got this right. All right, so in summary, in terms of various um, ancient measurements, so Aristarchus came up with the sun-moon distance ratio, which he calculated to be 20 to 1. Our modern value is 400 to 1. So this one admittedly was not very close, but Aristarchus did show that the sun is much, much farther um, from the Earth than the moon is. Aristarchus also showed that the moon's diameter is smaller than the Earth's. And this is fairly close. It did not such a a terrible job here. And then in terms of the Earth-Moon distance, again, Aristarchus came up with this value and was astonishingly close, I'd have to say. So again, a little bit of a mixed bag in terms of agreement between modern theory, but the key part here is not just the absolute degree of accuracy, but the methods that were being introduced, which were later refined and, of course, led to our modern values. These really stood the testament of time and really marked the transition into science. So, moving on, we'll next time talk about really the tension between two different models, particularly in the Middle Ages, and talk much more about why the geocentric model initially had more explanatory power, actually, than the heliocentric models, and about the Copernican revolution that really turned things on its head and the rise and surge in the explanatory power of the heliocentric models, with a couple of key figures, Tycho Brahe, Johannes Kepler, and ultimately Galileo Galilei, that really cemented the heliocentric model. All right, and then just to go into the sources here, so we have really like the first AI generated slides, which admittedly I had to tweak quite a little bit. But we have this set of sources you can check out. We have the second set of sources related mostly to those different myths. And then we have our third set of sources, which were primarily related to the Greeks in measurement. All right, and so that is, and then sorry, I guess so this was actually the same uh, round of AI, and then this third source was related to like our explanatory uh, scope, explanatory power, and simplicity criteria. All right, so that marks the end of today's class. I will be ideally recording much earlier in the week your ideally combined lecture for week 2, and around the same time you'll expect to see your quiz 2 set up. So if you have any questions, please do reach out. I will try to include more active discussions next time. And yeah, I hope that you had a great first week. And if you have any questions, again, you can email me. You can also attend office hours, which I've posted recently. So take care until next time.